The paper introduces Croissant-RAI, a machine-readable metadata format designed to enhance the discoverability, interoperability, and trustworthiness of AI datasets. This format extends the Croissant metadata format and builds upon existing responsible AI documentation frameworks, offering a standardized set of attributes and practices to facilitate community-wide adoption. The importance of high-quality data in AI technologies is emphasized, as poor data quality and documentation can lead to adverse downstream effects, such as biases, in AI applications. Recent studies have highlighted the real-world consequences of data-related issues, including gender-biased AI classifiers and issues during data collection that can cause AI applications to fail. The responsible AI community has identified data work as critical to the development of trustworthy AI systems, and seminal works, such as datasheets for datasets and data statements, have emphasized the importance of dataset documentation to assess and increase the trustworthiness of AI systems. However, current proposals for documenting AI data have limitations, including overlapping formats, the need for natural language documentation, and a lack of standard structure and integration with widely used tools and ML frameworks. Croissant-RAI addresses these issues by introducing a machine-readable format for capturing and publishing RAI-related data documentation, consisting of a set of attributes and properties that enable dataset users to easily find and utilize RAI metadata regardless of the platform on which the datasets are published. Croissant-RAI has been designed to be adaptable to evolving documentation requirements and is supported by a Python library and a visual editor. It has been developed through a community-led effort and is seamlessly integrated into major data search engines, repositories, and machine learning frameworks, streamlining the reading and writing of responsible AI metadata within practitioners' existing workflows. The authors provide a comprehensive overview of existing dataset documentation toolkits, highlighting their features and purposes. These toolkits aim to standardize dataset documentation, facilitating transparency, discoverability, and reuse. The introduction of Croissant-RAI, an extension of the Croissant metadata format, is designed to promote responsible AI development. Built upon established web publishing practices, such as schema.org, Croissant-RAI is engineered to improve machine learning datasets' discoverability, portability, reproducibility, and interoperability. The vocabulary is developed through a multi-step engineering process, informed by recent RAI data documentation frameworks and practical use cases. These use cases cover data design and collection processes, human and machine data labeling, data participatory processes, AI safety and fairness assessments, and data regulatory compliance. In the context of computer science, attributes refer to additional information, whereas properties describe the characteristics of an object. However, in English, both terms have similar connotations in defining characteristics of a real-world concept. The paper is organized to discuss background related to machine-readable metadata, the Croissant format, and state-of-the-art RAI documentation frameworks. The authors will present the vocabulary engineering process, use cases central to Croissant-RAI, and introduce the Croissant-RAI vocabulary with dataset examples. Finally, they will discuss tool support around Croissant-RAI and the implications of this work. Machine-readable metadata is essential for making data discoverable and easy to use. This metadata includes information about the data's repository, authors, or specific tags, expressed in a format that adheres to consistent structures to facilitate machine computation. The authors present a multi-step vocabulary engineering process for Croissant-RAI, a novel metadata format designed to enhance machine learning-ready datasets. This process involves bi-weekly sprint sessions, stakeholder engagement, and brainstorming sessions to define the use case and scope of the vocabulary. In examining existing data vocabularies, the authors identify overlaps and gaps, comparing them with other vocabularies. Participatory co-design activities and collaborative formulation of competency questions ensure diverse perspectives are considered. The implementation phase involves a bi-weekly sprint cycle to operationalize the conceptual models and core features. A conceptual framework is defined through consensus building and CO creation via collaborative modeling sessions. To ensure effectiveness and usability, the design is evaluated by annotating popular datasets. The authors discuss existing metadata standards, such as the Data Catalog Vocabulary, DCAT, and Schema.org, which enable interoperability and improve content discoverability. They introduce Croissant, a new metadata format for ML-ready datasets, designed to improve discoverability, portability, and reproducibility of ML datasets. Croissant extends Schema.org with additional layers to comprehensively describe datasets' attributes, resources, structure, and semantics. The authors emphasize the importance of responsible AI data documentation, considering aspects related to accountability, fairness, transparency, data privacy, and governance. They stress that data work should not be a one-off effort but rather maintained and updated to address potential negative downstream effects. The importance of dataset documentation for developing fairer and more trustworthy AI applications has been emphasized in previous works. Efforts such as datasheets for datasets, data nutrition labels, and data statements have encouraged data publishers to document data dimensions that may affect dataset use or the quality of resulting machine learning models. However, these approaches and tools require data documentation primarily written in natural language, lack a standard structure, and misintegration with widely used tools and machine learning frameworks, making data documentation difficult for machines to read and process. This work addresses these issues by proposing a machine-readable framework for capturing responsible AI, RAI, data documentation practices as an extension of the Croissant format, making RAI-related data documentation more discoverable, maintainable, and interoperable. The Croissant-RAI vocabulary engineering process involved community projects with experts from various backgrounds, referred to as stakeholders. The process was led through iterative and participatory co-design activities, defining the vocabulary through a comprehensive vocabulary engineering process. The process consisted of use case definition, comparison with existing dataset documentation vocabularies, scope definition, conceptualization of RAI extension and implementation, and evaluation through example annotations for each use case. Figure 1 depicts the different steps of the vocabulary engineering process, which began with bi-weekly sprint sessions engaging stakeholders from various domains and levels of expertise. The stakeholders identified and prioritized the attributes for the Croissant-RAI format, ensuring that the identified use cases were comprehensive, relevant, and aligned with the overarching goals of promoting data standardization and responsible AI practices. The process also involved a thorough examination of existing dataset documentation vocabularies to identify overlaps and gaps in relation to the Croissant vocabulary. Participatory co-design activities helped formulate competency questions that defined the scope and requirements of the Croissant-RAI vocabulary. These questions reflected diverse perspectives and priorities, acting as guiding principles to identify the key features and functionalities necessary to meet the objectives of the Croissant-RAI vocabulary. The conceptual framework for the Croissant-RAI vocabulary was defined on top of Croissant, ensuring alignment with use cases, stakeholder priorities, and compatibility with existing functionalities. A conceptual model of the Croissant-RAI vocabulary was developed, facilitating integration with Croissant and ensuring compatibility with existing functionalities. Finally, the effectiveness and usability of the Croissant-RAI metadata format were evaluated through participatory evaluation activities, including annotating sample datasets using the implemented features and gathering feedback from users to identify any usability issues or areas for improvement. Throughout each of these steps, participatory co-design activities played a pivotal role in ensuring that the features of Croissant-RAI were aligned with the needs and perspectives of diverse stakeholders. The Croissant-RAI vocabulary is a comprehensive framework that promotes standardization and responsible AI practices within the data documentation ecosystem. It facilitates the development of robust and adaptable domain-specific extensions, enhancing scalability and applicability across various fields. This vocabulary is guided by 5 use cases, including documenting the data lifecycle, characterizing in-depth data labeling and participatory processes, and providing critical information for AI safety and fairness assessments and regulatory compliance checks. The first use case focuses on the data lifecycle, encompassing stages such as motivation, composition, collection, preprocessing, uses, distribution, and maintenance. Documenting RAI-related properties encourages creators to reflect on the process and aids user understanding. Information includes creator, purpose, creation date, data sources, versioning, composition, processing, intended use, and maintenance. The documentation of the provenance and lineage of datasets derived from revision, modification, or extension of existing datasets is also relevant for this use case. The second use case centers on data labeling, which plays a central role in dataset creation for AI. Labels can be obtained through human input, such as labels from crowdsourcing platforms, or machine annotations like concept extraction. Details such as the platform used, number of human labels per record, rater demographics, and annotation tool characteristics aid in understanding dataset composition and facilitate efficient sampling. Information on the labeling process enhances comprehension of data creation, sample characteristics, and aids in assessing, replicating, and reproducing the process, thereby boosting data reliability. The third use case pertains to participatory data, where some machine learning datasets are created using fairly well understood, yet complex, data collection processes. Participatory data collection can involve various stakeholders, including data subjects, in the creation and curation of datasets. This use case highlights the importance of transparency and accountability in data collection, ensuring that datasets are representative and fair. The fourth use case focuses on regulatory compliance, emphasizing the need for datasets to adhere to legal and ethical standards. This includes compliance with data protection laws, privacy regulations, and ethical guidelines. Documenting compliance-related information aids in assessing whether a dataset meets specific legal and ethical requirements. The fifth and final use case addresses AI safety and fairness, which are critical aspects of responsible AI development. This use case encourages dataset creators to provide detailed information about potential biases, risks, and ethical considerations associated with their datasets. This information helps users understand the limitations and potential impacts of using the dataset, promoting more responsible AI development and deployment. In conclusion, the Croissant-RAI vocabulary provides a structured framework for documenting datasets, promoting standardization, and responsible AI practices. By focusing on various use cases, it ensures that datasets are transparent, accountable, and compliant with legal and ethical standards, ultimately enhancing the reliability and fairness of AI systems. This section of the research paper emphasizes the significance of documenting dataset provenance and metadata for responsible AI practices. It presents 5 use cases: data lifecycle, data labeling, participatory data, AI safety and fairness evaluation, and regulatory compliance. For the data lifecycle, it is crucial to document dataset creation, collection, and pre-processing to understand biases and limitations. The Croissant-RAI vocabulary, an extension of schema.org/dataset, provides attributes to capture this information, including data collection processes, design assumptions, and limitations. In data labeling, the vocabulary ensures label quality with attributes such as annotation processes, annotator information, and demographics. For participatory data, documenting information about data collectors, including demographics and platforms used, is essential. AI safety and fairness evaluation require information about potential risks and biases in datasets, including features for known and intended usage, and usage restrictions. The vocabulary provides attributes to capture this information, typically gathered at the item level and aggregated at the dataset level. Finally, regulatory compliance demands data-related information to assess a dataset's fit to privacy and current regulation laws. The Croissant-RAI vocabulary allows users to annotate this information in a structured way, including sensitive and personal identifiable information, data governance, and security measures. The Croissant-RAI vocabulary provides a comprehensive framework for describing datasets in a structured and standardized manner, enhancing transparency and understanding of the data used in AI model development. This vocabulary encourages data authors to consider ethical, regulatory, and technical aspects of their datasets, including data limitations, biases, and sensitive information. The application of Croissant-RAI is demonstrated through its use with various datasets, such as the HLS Bern-Scarsines dataset and the DICE's 350 dataset. The HLS Bern-Scarsines dataset, part of the Geospatial AI-ready datasets, focuses on geospatial data captured from spaceborne, airborne, and ground platforms. This dataset enables advanced location-based analysis and decision-making, particularly in solving complex problems like weather forecasting. However, it also raises ethical considerations in the acquisition and utilization of geospatial data, including potential biases, environmental impact, and privacy concerns. In the context of AI safety and fairness, Croissant-RAI suggests documenting data limitations, biases, and sensitive information within the dataset. This encourages data authors to reason about their data with a specific schema in mind, akin to the structure of proposals such as datasheets for datasets. For instance, location accuracy and spatial properties are vital to the credibility of geo-AI-ready datasets. Changes in local accuracy can have an impact on AI predictions, such as in AI-based crop yield prediction tasks where ground truth for validating the AI model is typically obtained from agricultural farms. The DICE's 350 dataset, on the other hand, focuses on evaluating diversity in conversational AI, documenting the great diversity within the annotators' profiles. The dataset is annotated by a pool of 104 raters, with a breakdown that includes 57 women and 47 men, 27 Gen X+, 28 Millennial, and 49 Gen Z, and 21 Asian, 23 Black, African American, 22 Latin, X, 13 multiracial, and 25 white. All raters signed a consent form agreeing for the detailed demographics to be collected for this task. The annotation task included 6 sets of questions that assess the legibility of the conversation, whether it is in English, comprehensible, on a topic that the rater is familiar with, or none of the above. The dataset also checks for harmful content, ensuring that the conversation does not directly facilitate serious and immediate harm to individuals or groups. The Big Science Root Corpus dataset exemplifies the complexities of creating a comprehensive, diverse, and inclusive dataset for language models. Notably, it highlights limitations such as the overrepresentation of pornographic text due to spam ads and the need for extensive preprocessing to remove personal identifiable information, p. The dataset incorporates multiple subratings specifying different safety concerns, crucial for developing AI models that accurately detect and mitigate potential risks. The Croissant-RAI format provides a structured way to describe datasets, enhancing transparency and accountability in AI research. This format includes information about data collection devices, preprocessing methods, and data manipulation protocols, essential for understanding potential biases and limitations. For instance, the HLS Bern-Scarsines dataset uses satellite images collected from specific devices and undergoes preprocessing to center detected burn scars, demonstrating the importance of detailed metadata in geospatial AI datasets. The DICE's dataset, focused on evaluating conversational AI for safety, emphasizes nuanced evaluations considering diverse perspectives. By incorporating features like rater diversity and detailed assessments across 5 safety categories, the dataset promotes balanced demographic representation among raters and fosters trust in using the data to create conversational AI models. The use of Croissant-RAI descriptions for datasets like DICE's ensures that critical metadata, including annotator demographics, is preserved and communicated effectively, enhancing the reliability and fairness of the AI models developed from these datasets. Comprehensive dataset descriptions, facilitated by formats like Croissant-RAI, play a vital role in promoting transparency, accountability, and diversity in AI research. By detailing data limitations, biases, and manipulation protocols, researchers can better understand the potential risks and limitations of their datasets, ultimately leading to more robust and reliable AI models. This research paper presents Croissant-RAI, a machine-readable format for capturing and publishing responsible AI, RAI, documentation metadata for AI datasets. The proposed format is designed to be compatible with existing data documentation approaches, making it easy to share, discover, and reuse. The vocabulary of Croissant-RAI has been derived from relevant RAI use cases and is illustrated in real examples from important domains and datasets. The paper also introduces the Big Science Roots Corpus dataset, a large-scale dataset collected from multiple sources that was used to train the Big Science Large Open Science Open Access Multilingual Bloom language model. This dataset is notable for its diverse composition, inherent limitations, and biases from the sources, as well as the pre-processing steps applied to ensure its quality. The paper discusses tool support for the Croissant-RAI format, including an extension of the current Croissant Python library and its web UI editor. This tool facilitates the community's adoption of the Croissant-RAI vocabulary by allowing users to input RAI attributes in JSONLD form. The paper concludes by highlighting the importance of future work, such as tracking the community's uptake of the Croissant-RAI vocabulary and collaborating with public and private partners to promote responsible AI practices. It also emphasizes the need for institutions to integrate RAI benchmarks into their frameworks to foster responsible AI practices. This research paper explores the concept of crowd worksheets, a novel approach to account for individual and collective identities underlying crowdsourced dataset annotation. It addresses the growing need for transparency, accountability, and fairness in AI development, particularly in data curation and utilization. The authors emphasize the importance of understanding social dynamics in crowdsourcing data annotation, which can significantly impact machine learning model quality and reliability. They cite studies highlighting issues with current practices, such as gender imbalance in medical imaging datasets leading to biased classifiers for computer-aided diagnosis. The Croissant-RAI property descriptions in Table 2 offer a comprehensive framework for dataset annotation and description. This framework is categorized into 4 groups: data lifecycle, compliance, data labeling, and AI safety and fairness evaluation. The data lifecycle properties detail the data collection process, including data collection type, missing data, raw data, and timeframe. Compliance properties focus on data imputation, manipulation, and pre-processing protocols. Data labeling properties provide information on the annotation process, including the annotation protocol, platform, analysis, and the number of human labels per dataset item. Additionally, the demographics of the annotators and machine annotation tools used are described. AI safety and fairness evaluation properties assess the dataset's social impact, biases, limitations, and use cases, including discussions on sensitive personal information, data biases, limitations, and recommended uses. This structured approach enables reproducibility, transparency, and accountability in machine learning model development, facilitating better decision-making and safer AI deployment.